Welcome back to Backspace Academy. In this lecture on databases on AWS, we'll start off by talking about the Amazon RDS service and how we can back up our databases, and also how we can implement failover and replication of our databases. We'll then look at the Amazon Aurora database, and then we'll look at the NoSQL database offerings that are available on AWS. We'll look at the Graph database, Amazon Neptune. We'll look at the data warehouse, Amazon Redshift. We'll look at the in-memory key store, Amazon Elasticache. And finally, we'll talk about the Amazon Quantum Ledger database, which is for critical transactional data. RDS, it runs a number of different database engines: PostgreSQL, MySQL, MariaDB, Oracle, and SQL Server. It also has its own proprietary enterprise versions of the MySQL engine and the PostgreSQL engine called Amazon Aurora. It's a platform as a service, so although you're launching instances like you would do with EC2, unlike EC2 where you're going to have to install that database software yourself and look after the updating and patching and all of that sort of stuff, RDS will look after all that for you. And all you need to do is launch that instance, and you don't have to worry about all of that management of that actual underlying operating system or the actual database software itself. Backing up your RDS databases is quite straightforward, and there are some options available for you. The first one being there is user-initiated DB snapshots of an instance. And by doing that, you have the control around when you take those snapshots, or you can have it left up to the RDS service to create automated backups to Amazon S3 for you. Now, by doing that, you can simply specify a backup retention period. By default, it will be enabled, but if you want to get rid of that, if you don't want to have an automated backup, you just set that retention period to 0, and you won't be getting automated DB backups. Now, if your instance is deleted, user-initiated snapshots are not deleted. But by default, automated DB backups are deleted when the instance is terminated. And you'll be given a note when you go to terminate your instance to state that. So you can actually, when you terminate an instance, you can create a final backup of that instance as well, if you like. And you can also have encryption of your database and its snapshots at rest if you like. If you are going to be deploying a production environment, it's always recommended to enable multiple availability zones, not only for your database, but also for your application that's going to be accessing that database, because it's no point an availability zone going down and having your database keep running if your application doesn't keep running as well, and vice versa. It's no point having your application in multiple availability zones if your database is not either. So the way it works, it allows a failover of a faulty instance over to a standby instance in another availability zone. So how does that work? Looking at the diagram there on the right, we can see that we've got two instances in separate availability zones, and they're receiving traffic from an elastic load balancer. Now those instances have an application that is going to be accessing an RDS database, and they're going to be accessing that through a database endpoint there, which we can see. Now, if you have multiple AZ enabled on your database, then AWS will implement for you. You don't have to really worry about this at all, but they will implement a standby instance in another availability zone. Now, if in availability zone A, that database goes down, the domain name for that endpoint will be changed to point to the standby instance. And you don't have to worry about that. It is managed by the Route 53 service, but you're not going to have to manage that at all. And you won't be able to actually even see those Route 53 entries for that, because it will be all invisible to you. It just happens, and happens quite well. So now that we've got our traffic being directed to availability or the instance in availability zone B, what will happen now is that the instance in availability zone B will be promoted as the master database or the master instance. And when the instance that is in the availability zone A, when that becomes healthy, it will go back online and it will become the standby instance, and it will be replicated or synchronized from that master or the new master instance in that new availability zone B. If you find your application is becoming very popular and your master database is receiving a lot of read requests, you can add read replica instances to your infrastructure that can respond to these read requests. And that is supported for Aurora, PostgreSQL, MySQL, and MariaDB. It's not supported for Oracle, and it's not supported for Microsoft SQL Server. You can have multiple read replicas, and with Aurora you can have up to 15. If you're not using an Aurora cluster and you're using standard RDS instances, each one of those read replica instances that you launch will have its own separate database endpoint. And so that creates a problem, because how do we distribute requests from our application through to these read replicas? Because our software will probably only want to use one endpoint to access that data. So there are a number of options available for you to address that problem. Obviously, the first one is to use an Aurora replica, which will have one database endpoint, or you can implement a solution in your software. So each time that you want to access that database, you can use a different endpoint to access that database. And by doing that, although it's not going to be perfectly balanced, you're going to be taking advantage of all of those available instances. The other option is to use the Route 53 service, and you can actually create an internal domain name that will receive requests for a specific domain name that you specify, and it will direct those using weighted round robin or whatever you want to use to individual instances. And finally, you can implement your own load balancer using HA proxy running on an EC2 server. But that's going a little bit too advanced and a little bit too complicated. Most people just implement a solution in their software or implement an internal domain name using Route 53. Amazon Aurora is the enterprise solution for RDS, and it provides the MySQL and PostgreSQL compatible database engines, and it provides a significant cost over using a commercial database. It also provides a significant advantage in performance over standard RDS on MySQL and PostgreSQL. Unlike RDS, where you're launching individual instances, Aurora will launch a cluster of instances, and the advantage of that is that it will have a single database endpoint, and the requests coming to that single reader endpoint will be load balanced automatically by the Aurora server. So it solves that problem of using RDS read replicas and routing all of your requests to those multiple read replicas. Aurora will look after all of that for you. Aurora, it will scale your performance up or down simply by vertically changing the instance type, or horizontally by adding up to 15 read replicas. If you have a sporadic demand for your database and it's just not consistent, it's unpredictable, then you may want to consider using Aurora Serverless. So that, as the name suggests, is a serverless environment of Aurora, and you pay by the second, and it will shut down when it's not needed. DynamoDB, it's a NoSQL database, and it consists of tables. For example, we could have a table of all the persons, attributes for those table, for example, the person's first name, last name, etc. We can have individual items. So that is when we put in a record or an item. and so that would have the person's name, their last name, etc. We can also define partition keys and an optional sort key to help us to access our items quite quickly as well. So there's just an example there of a people table. And so within that people table, we have attributes of first name, last name, email, etc. And then we have 2 items that have been put into that table for Bill Smith and Joe Vlogs. Now we might want to regularly find people by their last name. So a good partition key to define would be last name. Or we may find that we also want to quite regularly look for people by their email. So we could have a partition key of last name and also have an optional sort key for email. Now there are 2 different pricing models for DynamoDB. If you know what your capacity is going to be in the future, then you can provision that capacity, and that is provision capacity. Or if you want to leave the DynamoDB service to expand and contract that capacity for you, then there is an on-demand capacity model as well. Provisioned capacity is where you specify the number of reads and writes per second that you want. And so if your application is pretty consistent, and you're going to get a reasonably consistent demand for reads and writes, then that's a good way to go with provision capacity. But if you find that the capacity changes over time, it might be seasonal, it might one day be a little bit more or a little bit less, then you can adjust that using auto scaling. So just in the same way as that you would have auto scaling of EC2 servers, you can also have auto scaling of your provisioned DynamoDB capacity, and you can trigger that based upon a CloudWatch alarm. The use cases, if you've got predictable traffic, of course, then provision capacity is great for that. If you find that that capacity varies, but doesn't really involve spikes of traffic, if it's consistent and ramps gradually, then auto scaling along with provision capacity is great as well. The great advantage of using provision capacity is that if you know what those forecast costs are going to be, you can control those costs as well, and you're going to get the savings from that. If you find your database has an unpredictable demand, or that demand is quite spiky or whatever, DynamoDB On Demand is a good option and allows to automatically scale up and down based on demand. And so there are a number of flexible billing options that are available for this, and it allows you to serve thousands of requests per second without having to worry about capacity planning. And you simply pay per request for those read and write requests. You can use on-demand capacity mode not only for new tables, but also for your existing tables as well. Amazon Document DB, introduced in 2019, has been much awaited by the AWS community. And that is because prior to this, the really only powerful solution for NoSQL was to use DynamoDB. And unfortunately, MongoDB is the most popular NoSQL database out there, and it has a really rich command set. And migrating legacy MongoDB applications over to DynamoDB is a real headache. And I've had to work with a lot of students and a lot of people in the past in doing that, and it really, really is not an easy thing to do. So with Document DB, you don't have to worry about launching your own EC2 instances, managing the software on those EC2 instances, looking after load balancing, all of that sort of stuff. It's a service that is provided, and it's a service similar to Aurora, where you launch instances inside of a cluster of up to 16 instances, with one of those being a primary, the rest of them being replicas. It provides great availability of 99.99%, and it provides a replication using 6 copies across 3 availability zones. And furthermore, it will back up your data to Amazon S3 continuously, and it will provide up to 35 days of point-in-time recovery. And when that is going on, there is no downtime or performance degradation either. Amazon Keyspaces is an Apache Cassandra compatible NoSQL database. It's compatible with the Cassandra query language, or CQL. And like DynamoDB, it has two operation modes. The first one being provision capacity, where you can specify the read and write capacity. If demand exceeds that, then requests will be throttled. Or you can have an on-demand mode, where AWS will manage that capacity automatically for you. Amazon Neptune is a graph database, and they are optimized for relationships between data. If you want to have a look at a really good example of a graph database, you can have a look at the ICIJ, or International Consortium of Investigative Journalists database, and that is a database of all of the money laundering individuals, or suspected money laundering individuals in the world. So that is a great way to actually visualize all of the relationships between these different lawyers and different companies and different tax haven companies and whatever. And so that was using Neo4j. It wasn't using Amazon Neptune, but the principle is the same, of using a graph database to organize these relationships between massive amounts of entities. These graph structures consist of nodes, and they are your individual data entities. And then we have edges, which define the relationships between those entities. And we also have properties that can represent and store data about those nodes. And you can query an Amazon Neptune database using Gremlin or SparkQL. If you've got massive petabytes of data, then Amazon Redshift is your best solution for that. It's a fully managed big data warehouse, and it's based upon the PostgreSQL engine. It's specifically designed for online analytical processing and business intelligence applications that require very complex queries over large data sets. A Redshift cluster, it consists of a set of nodes which have a leader node and one or more compute nodes. And you have the choice of type and size for those nodes. Elasticache is a fully managed in-memory data store. So it provides really high performance, low latency data access for your content. The reason it does that is that because it's accessing that data directly from memory. It's not going back to an SSD to collect that data. So the response rates are going to be very quick. You have a choice of the Redis or Memcached database engine. It can be used on its own as a standalone key store database, or it can be used in front of another database, for example, DynamoDB, to respond to requests for regularly accessed content. So looking there on the right hand side there, we've got a diagram there with an application running on EC2. And so it wants to get the access to its regularly used content quite quickly. So its first request is going to be to Elasticache. Now, if that data that it wants is not located in the Elasticache cache, then it will look for it in DynamoDB, which is the master database there. And we'll have a Lambda function, which will be automatically synchronizing between DynamoDB and Elasticache for that regularly used content. So by doing that, you're going to get the best of both worlds. You're going to be getting a really good low-cost solution with DynamoDB, and you're going to get very fast access to regularly accessed content using Elasticache. Now let's just say you've got a really popular game, for example, Fortnite. and you want to keep track of your top 100 scores across all of your users, and it might be millions of users, but at the same time, you want to keep track of all of them, not just the top 100. So what you could do is that you could store that top 100 in Elasticache, because they're going to be regularly accessed. People want to see who's on the top 100 list, for example. And then the individuals that are not popular, that are not on that top 100, could be stored in your back-end database. So then you're going to have the best of both worlds. Amazon Quantum Ledger Database, or QLDB for short, is a fully managed ledger database, and it provides an append-only, immutable and transparent journal. What that means is that you cannot delete a transaction after it has occurred. You can append a transaction, but any changes to any transaction will be visible. And it provides built-in cryptographic verification of transactions as well. And it's very good for very critical applications, for critical accounting applications, for health and other sensitive information. The way it works is your sensitive data will be put into the ledger database, and a journal will be kept of all transactions. And that journal will be cryptographically verified to ensure that it is always correct. And there will also be a current state and indexed history around that journal, and which you can view through the management console as well. Okay, that brings us to the end of the lecture on databases. I hope you got a lot out of it, and I look forward to seeing you in the next one.